I learned something that last panel that I guess I hadn't appreciated ahead of time, which was that we can actually really be in the driver's seat here if we choose to engage that way. It sounds like, given the thrashing in Sacramento, there is a lot of opportunity to inject engineering and science, but it's going to have to come through the staff and from us directly. So I think that makes for an interesting place to start this discussion on regional impacts and integrated long-term planning. My name is Paul Wennberg. I'm the R. Stanton Professor of Atmospheric Chemistry at Caltech. And recently I was appointed the director of the new Lynn Center for Global Environmental Science. So as I mentioned in my opening comments this morning, California really faces enormous challenges, and the large population increases are anticipated. AB 32, which we've just heard about, envisions large reductions in carbon emissions. As we've just heard, Sacramento really has only now just begun to understand the challenges of implementation. Carol Carmichael, who helped us put the program together here today, told us a little bit in a student group that we have here about the efforts of the city of Pasadena to try to understand how to comply with AB 32. So these discussions are going on throughout California's cities and towns, and I think there are lots of opportunities for those who are interested to help engage in that process. So today, this panel, what I hope we will get to are some of the questions about how will global climate change impact California? How can we provide sufficient clean water while the population of the arid Southwest is growing so rapidly? How can we reduce seismic risks? All of this through our own actions as scientists and engineers and data users. And can California continue to make progress on clean air while the global atmosphere becomes much more polluted? And these are some of the questions that I hope we'll get to. I have some that I've put together, but I hope the audience will also provoke some of the conversation. So my own research is in the area of atmospheric chemistry, so I'll try to take on this last question about the polluted global troposphere. Can I have the next slide? This is a figure that I got from David Parrish at NOAA, and what's shown is data, ozone data, in situ observations made in the northern hemisphere, but far, far away from any urban centers or cities. So going back to 1960 and through 2000, after 2000, you can see a growing concentrations of ozone globally. These are so-called background conditions, and they're the starting point for what happens in any city or state. So as the clean air that comes into California from the Pacific becomes more polluted, we must work even harder to meet air quality standards and goals. In some areas of the Central Valley, research now suggests that completely in the absence of any local emissions, we will have exceedances, simply because the free troposphere coming in from the Pacific is becoming so polluted. Over the last decade, NASA and JPL have placed into orbit wonderful new sensors that monitor the chemical composition of the lower atmosphere. The TESS instrument, for example, is making the first global measurements of lower tropospheric ozone. Nitrogen dioxide, or NOx, can be mapped at ever finer scales. Have the next slide, please. This remarkable image sent to me from Ron Cohen is the NO2 concentrations in the state of California, observed by the OMI instrument on the NASA's Aura platform. If I go to the next slide. This is the image of NO2 now several months average over the Los Angeles basin. The little dots are where the AQMD currently has air quality monitoring stations. You can see the unprecedented scale for which we are now gathering chemical composition information. Such data, which is now just being used in our estimates of those, basically the model simulations that we're doing, should greatly aid in the engineering improved air quality by allowing the state and regional agencies to optimize their design. As was mentioned earlier by Barian, we have a great need to produce similar sorts of data for greenhouse gases if we hope to do treaty verification. There are also, of course, many observational challenges. Many of the sensors that we've come to rely on, such as OMI, are now aging. Efforts to maintain continuity have pretty much stalled. Just this morning in the Washington Post, there's a glowing article about Metric, which is a data product that uses primarily Landsat thermal imagery to estimate evaporation of water from fields and wetlands. According to the Washington Post, this product has now actually become quite essential for water resource managers in the West for planning, and they're even discussing using it in future treaty verification. Yet currently, that thermal sensor is not included in the Landsat data continuity mission, and NASA is under significant pressure to find this extra resources to do this. So I think when we think about the space-based sensors that we have today and their use in long-term planning, there's a tension. There's a tension between NASA's entrepreneurial sentiment, the idea that we must build new and improved sensors to go after more and more different things, and the needs of the community to maintain record continuity in order to evaluate changes over long time scales for such processes as regional planning. So with that, I'd like to introduce our panel and offer each their opportunity to provide their perspective. So John Chen is the Executive Director of the Los Angeles Department of Water and Power, Consumer Services Division, and he also leads the development of the Clean Technology Research Center, and I believe he'll tell us a little bit about that today. Andrea Donnellan is NASA's Applied Sciences Natural Disasters Program Area Lead. She's also a geophysicist at NASA's JPL and a research professor at the University of Southern California. Steve Margulis is Associate Professor in the Department of Civil and Environmental Engineering at UCLA. He has worked extensively on monitoring of snowpack in the Sierras. And finally, just back from Tibet, is Susan Ustin, who's the professor of the Department of Land, Air, Water Resources at the University of California, Davis, and is the director of the Center for Spatial Technologies and Remote Sensing, CSTARS. So with that, I'll ask you each to prepare your prepared remarks.
Good morning, and thank you, Paul. First of all, I'd like to thank the event organizer for giving the opportunity to speak here. It's always a special place. I did attend the summer school here one time, many years ago, so it's always great to come back. Before I get started, how many of you live in the city of Los Angeles? Can you just raise? What? At least city of Los Angeles. Yes. Great. Well, we have a lot of great, exciting things that's. Maybe we can start a dance line. That's good music, though. Oh, he's a hydrologist? Okay. Anyway, the mayor of the city of Los Angeles, Antonio Villaraigosa, has set very large goals for the Department of Water and Power. And Department of Water and Power is the largest municipal utility in the nation. However, it's undergoing a tremendous transformation. We've been asked to, just give you a perspective, for the past 50 years or so, we've been using coal for energy generation for almost 40% of our portfolio. By 2020, 40% of energy resource will be coming from renewable, such as solar, wind, and the geothermal. So that's a big transformation. Earlier, the panel talked about there's a lot of hurdles have to overcome, costs, transmission lines. Those are the very critical things that we have to overcome in order to implement this 40% goal. I think a lot has been talked about solar, wind, and the renewable in general. But for California, and I think that the main issue is still going to come down to water. I think, again, earlier somebody mentioned, I think was Dr. Moore mentioned, water. We can find solutions for energy, But if we run out of water, there's really nothing you can do about it. So with all the talk about renewable, but the underlying issue is the water. So that's why we are looking to meet the future growth of City of Los Angeles for the period between now and 2030 through recycle or conservation of water. That's about 100,000 acre-foot, which equivalent to serving about 400,000 additional people in the city of Los Angeles. Next. If we do get a chance to successfully implement the renewable up to 40%, there will be a lot of technical issues. Obviously, wind is not dispatchable all the time. It depends on the weather. Same thing with the solar. And be able to integrate all those resources together and meet the demands of our customers is going to be a challenge. So a lot has to depend on the weather. So I have seen quite a bit of technologies that's existing with JPL and other universities. I think be able to forecast the short-term and long-term weather patterns are very important as part of this integration, I guess, effort. Next page. On the water planning side, we have a panel here, a specialist that looks at the condition of the Eastern Sierra. The chief technologist at JPL did a presentation for us some time ago at Department of Water and Power, Paul. Paul mentioned that he showed us a slide which predicts the availability of water from Eastern Sierra 70, 80 years from now. It's almost zero. So I was quite shocked. I said, what do you mean it's almost zero? It means there will still be snow. And he told me, yes, there will be snow. But the problem, because of the climate change, the snowpack is going to melt so fast, unless you have a reservoir that's built right there, you're not going to be able to capture any of the waters. And that's a huge, huge issue, because we get a lot of water from the Eastern Sierra. And because of the draw in California, we are getting less and less water from Northern California, Southern California, all the snowpack. In addition to that, we are also covering our reservoirs. We're getting rid of our reservoirs because of regulations, and we're building storage tanks, but be able to control the supply and demand issue, whereas before you have a large reservoir, it doesn't matter. You want water, just release the water. But the tank size are limited, and also there's a limitation on how fast you can pump those tanks. So be able to forecast the weather, to look at the resources where the water is coming, and how you dispatch it depends on the demand, is very instrumental to the water supply for the future. 2 years ago, I had a conversation with Ken and Dean from JPL. Dean is sitting there in the audience, and we talked about partnership. There's a lot of brain power in this room right here, sitting here. But we also, in addition to JPL, Caltech, we also have UCLA and USC. We wanted to come together as a group. Department of Water and Power is the largest municipal utility in the nation, as I mentioned before. We are spending billions of dollars on water conservation, recycling, groundwater recharge, capturing of the rainwater, and renewable energies. We wanted to be able to provide a test bed for all the new technologies that comes along. Before we make those investments, as the previous panel talked about, we want to hear from the experts. What's out there? It's okay to invest $1 billion on this technology. If something else is coming, we would like to know about it. We would like to know ahead of time. So we created this partnership, and the mayor has signed with the director or president of JPL and our general manager. Since then, we have submitted $300 million of funding for the stimulus package that address smart grid, storage, energy storage, electric vehicle. We touched a little on earlier regarding the issue of transportation, and many other projects. Some are infrastructure, some are demonstration. We talked about two things: funding. There are fundings. Even though the state, as it is right now, in fiscal conditions right now, they are funding from the federal government. And we're still spending money to get those projects off the ground. Partnership. Earlier, somebody mentioned, can we make sure that we don't compete so much that we're not working with each other? I truly believe that if the presidents of the universities, all universities, can come together and want to work together, and I'm sure the professors and researchers can also come together, because only when we come together, we can compete at the national level. And it's very, very, very important that we come together as a team and go compete at the national level. So there are some other examples of the things we're already doing for the water sensing, for controlling the irrigation system, basically putting a camera onto the helicopter to monitor water irrigations, Owens Valley and snowpack conditions. So we can touch upon that a little bit later, but that's it. Thank you.
Put the first slide in. It's not up yet, but when it's up, I put the first slide in after the first session. I didn't want to have a lot of words, but I wanted to talk a little bit about the purpose of NASA's Applied Sciences program, which is bringing the spaceborne and airborne and modeling and analysis capabilities down to the end user, as well as leveraging some of these organizations that we already have. I sit on this White House Subcommittee for Disaster Reduction, and they've given a lot of thought to grand challenges in disaster reduction, and NASA has some clearly defined roles there, and the other agencies do, and it flows down very nicely. So what we want to do is make all those connections between these stovepipes so that we have a nice integrated system. Next slide. Just show you some movies. Is it going? There we go. On your left, we have Virtual California. It's a simulation in the computer of 1,000 years of earthquakes showing how earthquake faults interact. So we have the San Andreas Fault. You can see the coastline is very faint there, and we go from the Salton Sea up to the Bay Area. That small discretized blinking area is the creeping section of the San Andreas Fault. And then you see occasionally large earthquakes, which are these large fringes. They're just like topographic fringes on a map showing displacement. You see sometimes small earthquakes clustering in time, other times large earthquakes clustering in times. And what we have in here, we just drive it with a plate tectonic motion, and we have frictional parameters on different faults. And what you can learn very quickly from this is we don't have nice, regularly repeating earthquakes. They interact very differently. We can do statistics on these fault systems and understand things like, out of this particular model, that the Landers earthquake type events typically are followed by a San Andreas type event within 20 years. We don't have it the other way. The Landers events aren't followed by the San Andreas events. And so we can learn how future earthquakes may occur based on previous earthquakes. Next slide. Next step over. We have over here is Mount Etna. These are interferograms from INSAR, a European satellite, showing how Mount Etna inflates when there are eruption events, which are marked by these red vertical bars. The volcano deflates again. And so you can get a sense of the things we can observe with spaceborne observations that we couldn't in the past. You could apply this to Mammoth. It's being flown with an INSAR instrument on an airborne platform right now, and eventually one of our decadal survey missions. Next slide. I just want to talk about the need for simulations. In the event, NASA is a research agency, but in the event of a natural disaster, we want to apply what assets we can, as long as the platform's not in Greenland or something, which it may be. But it's important, too, to participate in these simulated exercises, because we learned very quickly where all the gaps were in flowing from the spaceborne and airborne technologies down to the end user. For example, the planes parked at Dryden were at JPL. The operators need to get to Dryden in the event of an earthquake, and the San Andreas Fault is now moved 20 feet. So you got to bring the airplane down to Van Nuys. And then we passed the data through the chain of command. We simulated the data because the platform wasn't flying at the time, all the way to Gerald Bawden, who presented it to the State Operations Committee, and they didn't know how to read an interferogram. So there's an educational process. So we need to fix all these broken links. Next slide. Just want to talk a little bit about water. This is, on the right, the levee system can be monitored with radar, and on your left, on your right, this is ground surface motion, which is mostly affected by aquifer discharge and recharge seasonally. And so again, you can measure these things that we couldn't see before. They're not seismic, so they're quiet, but we can detect them with the spaceborne technologies. Next slide. just wanted to, again, reiterate, we need to go from the global spaceborne platforms down to my street 2 weeks ago. It's not good when you read about your street in the international news. But there are a lot of data latency issues. The web pages were updated like every 8 hours. It's not very useful. The maps were inconsistent as to whether my house had burned down or not when I was evacuated. So we need to fix that. We need to improve the latency of the data. And just to go to the next slide, I just wanted to end it with the need for long-term planning. I think the picture says it all. We have our future generation to worry about. And just to put in a plug, in January 12th to 14th, we are having a decadal survey missions applications workshop. Hopefully, a lot of you people can come. We need to worry about the data issues for Google. How do we make it useful? And how do we make sure that the applications are met out of the missions from the decadal survey? I'll stop there.
So again, just want to thank everyone for the invitation and for coming to this very interesting symposium. I'm very interested in the topic myself. I'm a hydrologist, so I'm interested intellectually in the cycling of water on regional and larger scales, but I reside in a civil engineering department. So we're very much interested in how we can translate these large-scale, study these large-scale problems and their solutions and translate those to actionable science for society. So I just have a couple slides here to kind of illustrate one of these issues, which is not unique to California, but certainly is a good example. So one of the things I work on is snowpack. And we've heard a lot today about how California can have such a large impact because of its economic power and population. Another very interesting aspect of California is its geographic diversity. So we get to study lots of different types of problems, from remote mountain areas to urbanized areas to coastal areas and so on. So we've heard a lot about how water is very important, and so one of the areas I study is snowpack in the Sierras. And so just, again, to give a very brief background, most of you are very familiar with this, snow is very important in many areas. A large fraction of the population gets a majority of their water from seasonal snowpacks. And because of the physical processes, these snowpacks often occur in remote mountainous regions due to orographic precipitation. So California being a prime example of that, much of our water is stored seasonally in snowpacks in the Sierras. And so it actually provides a very nice test bed for remote sensing, because despite the fact that in-situ networks in California and in the Sierras are quite good by global standards, the length scales at which snow varies generally is such that the snowpack is undersampled. So it provides a great opportunity to really show the ability of remote sensing to provide added value and ultimately translate that to some actionable science. So next slide. And so to kind of bring this to remote sensing, I think one thing that's important is to, as we aim to bridge the gap, is communicating what it is we're measuring and the associated uncertainties with that. So in terms of how do we remotely sense snow, these are just two examples. One is using visible channels, and there are trade-offs between the various ways we measure this. So this is an example of fractional snow-covered area from the MODIS sensor, which provides pretty high-resolution maps, as we can see. So we see very clearly the correlation between fractional snow-covered area and topography. But it's really just giving us a reflectance, whether or not snow is there more or less. So it's not telling us how much water is there, which for a water resources engineer, for Department of Water and Power, or MWD, they want to know the snow-water equivalent, how much water is there. On the other hand, we can use microwave measurements, which is shown in the other slide, which is much more directly connected to the amount of water mass stored on the ground. So it's much more directly connected to what we're most interested in, at least from a water resources engineering perspective. But as you can see from the image, it's generally available at much, much coarser scales. So while you can see in this particular image some signal from the Sierras, it's certainly not at the scales of variability that we typically see in snowpacks. And so there's these trade-offs in remote sensing between various parts of the spectrum. There's many, many other measurements in the microwave as well that we can make, each of which have their own connection to the snow water equivalent. So the real challenge as scientists is to tease out from these various data streams what we're interested in, namely snow water equivalent. And in doing so, in terms of transferring that to policymakers, doing, I think, a better job of communicating the uncertainties associated with those various data streams and how those uncertainties propagate to the estimates that we're able to make. So I'll just leave it at that.
I would start by saying also thank you very much for inviting me to talk. I'm an ecologist by training, and I work on a whole variety of environmental problems from very local issues to large-scale global ones. And I want to talk about using remote sensing data to address regional environmental problems. So specifically, I have an example from the Sacramento-San Joaquin Delta. Our delta system's about 1,100 square miles of area. It's the confluence of the Sacramento and San Joaquin River. And I think by most people's opinion today that the delta is really in ecological crisis. So it's a good system for using more remote sensing data to try to understand because of the scale of the problem. This is a Landsat image. It's a color infrared image, so everything that's vegetated is red. So, and the more vegetation, usually the darker red that it is. The area covers not the full delta, but more or less the square that's in the little insert up on the left. And you can see it's comprised of lots of channels that go through the delta forming islands. There's something on the order of 65 or 70 islands in the delta, and they're created by levees that were built starting on the turn of the century, last century, and pretty much finished by the beginning of the 1930s. And so today they're all in a kind of a state of deterioration, and there's a lot of concern about the failure of the levee system. The water supply that the delta provides water for about 2/3 of the population of the state. And so this could have a major impact. It also provides the water supply for most of the irrigated agriculture in the state. So the stability of the system is of high importance. The last levee failure we had was in 2004 in June on a very nice day without a huge overflow or any other storm surge or any other symptoms. One of the large levees broke and flooded about 12,000 acres for no obvious reason, that no engineers have figured out why that particular levee failed that day. So one of the issues the Delta faces right now that the Corps of Engineers is trying to make a decision. Do they implement the national standards for the levees in California, which require removing all of the trees from all of the levees? After Katrina, the Corps of Engineers has been suddenly found it important that they implement their national standards. And the trees in California Delta levees are probably the last of our riparian forest. And since we have winter precipitation patterns in California, it may be that the root system in the trees actually helps stabilize the levees as opposed to their standards, which say that the root systems provide conduits for water flow through them. And hence that's why they want to get rid of the trees. So one of the ways that this remote sensing could contribute to this problem, and actually we've been working with the state on this, is using high spatial resolution airborne LiDAR data over the entire levee system and getting detail maps of the shape of the levees, whether they've slumped or whether they're, what they look like, and the location of all of the trees, and trying to understand whether the trees are contributing to potential failures or not. As of today, that it's pretty likely that the Corps is going to implement this standard regardless of the consequences, even though there are a number of endangered species that depend on these riparian forests. And there's another secondary consequences. When they remove the trees, it will cause a lot more radiative heating of these small channels in the levees. And we also have a very big problem in the levee system because of a rapid decline in quite a number of the native fish in the delta. The delta smelt was put on the court-ordered limit of water supply to the agricultural system in the state last spring because of low flows likely causing the extinction of the delta smelt. There's also a potential relationship to the decline of the Chinook salmon runs. Both the spring and the fall runs are endangered. So if you remove the trees, you cause more heating of the surface water, and that has a potential also effect on the ecology of the fish populations. So those are just a couple of the reasons. The delta varies temporally on really all kinds of scales. It's a tidal system, so we have 2 high tides a day that come push the water back and forth. It sloshes around in there. All of the channels are controlled by the Department of Water Resources through active management of the water systems. And that's another thing that's being reviewed right now by the state, is whether they'll implement the peripheral canal, or nowadays called the cross-delta conveyance system, I think, or something like that. One of the concerns about the delta is that perhaps the current system that keeps the water, the flow levels, less saline in the summer might be one of the causes of either the spread of the invasive aquatic weeds in the water system through the delta. That sort of concurrently happened with the rapid decline of the fish in the last 10 or 15 years, that the water flows have too low a salinity, and therefore you get it makes it more suitable for invasive aquatic weeds, and that somehow has some interactive impact with the fish population decline. So that's another thing that can be looked at with remote sensing data. So the little image on the bottom left shows an example of that. And just go to the next slide, then I'll quit. And this shows we've measured with airborne remote sensing for 5 years the change in the population of submerged aquatic weeds in the delta. So for this particular example, the darker colors, the weeds were there 5 years ago, and you see as it gets lighter and lighter that's the spread of the weeds into different positions as it spreads out from its source population outward over that 5-year period. So having remote sensing data is really the only way to document this kind of change, because you can't do it in the field and you can't do it any other way. So I'll stop.
Well, thank you very much. Certainly the theme of this panel is water. And I'd like to start there and ask essentially all of you about the prognosis for California water. And maybe Steve could start. There's been sort of a, well, we heard John mention that the chief technologist, Paul Diatakis at JPL, has suggested that there will be very little snowpack in the eastern Sierra. Maybe you could comment a little bit about on how we might know that, how well we know that, and then we'll move on to talk. Maybe Andrea could address a little bit of the question of the aquifer storage. Obviously, if there's much less snow, but we still have, of course, the seasonal rains, we're going to need to store that water, and there's been a lot of suggestion of places to put it. and groundwater recharge is one very attractive position. And then maybe, John, you could talk a little bit about how you see the future of water delivery and storage, and whether you think the planning, because you have to think on very long timescales, what the planning situation is in water. And then finally, we'll come back to Susan and the outlook for the Delta, as it is, of course, as you mentioned, 2/3 of the freshwater resource for the state.
Okay, I guess I'll start. So my perspective of what I've been working on is focused more on retrospective analysis, and I would argue that in terms of snowpack, again, as I mentioned, while the in situ networks, the snowtail networks in California, in the Sierras, are quite dense by kind of global standards, they really do undersample the snowpack, and that we don't really have a good idea about the spatial and temporal variability, at least in an explicit sense. We have measurements that either give us point scale measurements of snow water equivalent or runoff, which give us an integrated metric of the melting snow. And so from a remote sensing perspective, I think we're fortunate, although we haven't maybe mined it well enough yet, that we have a microwave record that goes back about 30 years, as well as a visible record which goes back a similar length of time. So I think there's a lot of retrospective analyses we can do, in addition to ones that have been done using these in situ sensors to look at trends of snowpack in terms of snow water equivalent or earlier melt and so on, to really get a better handle on how the snowpack has been behaving, at least over the last 30 years, which by many people's measures maybe not long-term enough, but as from a remote sensing perspective, that's pretty much as good as we get in many respects. And certainly in doing so, we will be developing tools which could be used in kind of real time going forward to characterize snowpack, which may in fact be changing. And of course, for those who study snow, and we like to talk about how it varies over such short spatial scales and in time. If it goes away, of course, our problem becomes much easier to study. All the variability goes away. So, but being able to develop these tools to really look explicitly at snowpack and how it's evolving, I think will elucidate the current situation, the past situation, and give us insight going forward.
But John has to plan for 50 years now, and so is it just we need to keep studying, or can you say something about snow storage?
I think the retrospective analysis can also be used to validate the forecast models which are used to predict snowpack going forward. So, but I agree, the issue is an important one because our infrastructure is so set up for this large spring pulse melt. So I think it's certainly a challenge, and it relies on using these atmospheric models to do these predictions going forward, which themselves have uncertainty. So I think in some ways the snowpack situation does look grim going forward, but I think remote sensing gives us some insight, at least in the near past and going forward, as to how it may in fact be changing and how we could then better plan for those changes.
Andrea, do you want to comment?
I'm not a hydrologist, but my understanding is that when these aquifers discharge, there's compaction that occurs, and so they can't be recharged to the same level. And so here's a place where remote sensing can Gerald's nodding, that's good. Remote sensing can tell us, we can measure what the ground surface is doing and then model what's going on in the aquifer to understand how well we can recharge them if we need to plan for other areas or make other plans.
Okay, well, I just want to make a comment that as we go forward, there's two things I think is fairly certain. One is that we'll get less water just because the population grows and the demand will continue to grow, but the water is getting less and less. The other thing is it will get more expensive. Right now it's still very cheap, but as years goes on, it will get more expensive. It's just a matter of supply and demand. one of the things we're focusing right now, obviously there's a lot of technology out there, but one of the things that we really have to do better at is through recycled water. We currently have about 1 to 3% water that's being recycled. Just give you an example, Israel, they recycle about 70% of the water that they use. So we have a long way to go in terms of building the pipelines to the treatment plants for sanitation, and also for all the new development projects like Playa Vista. As a matter of fact, 10 years ago, I was part of the negotiating team where we asked Playa to put dual plumbing to the new development project, and majority of that has came to fruition. And I think this is one of the community that has all the recycled water dual pipe with the potable water. Conservation. We have made a lot of noise about conservation for the past few months. Since the mayor asked the engineers to reduce consumption in September of 2007, as of last month, overall water consumption has reduced by more than 20%. 20% is significant. And there are there's a team of people that works for me that actually goes out and write tickets for people that violate the water irrigation rules only on Monday and Thursdays. So far, they have, responded to about 14,000 complaints and issued more than 5,000 warning tickets. The good thing is that the monetary penalty doesn't kick in for the second or third time offenders. But all those activity has made a huge impact on the short-term water conservation initiative, just so that we can meet the drought condition that we have right now. But longer term, City of Los Angeles has replaced over 1 million toilets since in the 1990s. That basically kept the water consumption pretty much flat for the past 10, 15 years, even though the population has grown somewhere between 500,000 to 1 million people. And we needed to continue to do that. I do have a goal to replace additional 60,000 toilets for the next 2-3 years. That will be a longer-term conservation. Once you implement that, then the conservation will continue. Same thing, we also focus on, for example, urinals, waterless or even one pint. It's just unbelievable how much water is being used, especially, for example, Staples Center is one of the first ones that did that. But each time I go to a game, I see people just comes out and go use the restroom, but amount of water that's being used it's huge. Those type of things, along with the building codes. Whenever you build a new building, we now have new stricter building codes, so that so all the new buildings will try to capture rainfalls, will implement the water conservation measures. So those are permanent solutions that will address the long-term water shortage in Southern California. So those are the things that we're doing, try to address the immediate and the long-term needs of the water resources.
Does the city of Los Angeles contemplate desalinization as a source of water?
Yes, that question has been came up multiple times. For example, again, going back to Israel, they are building some of the largest plants over there because simply they have no other choice. But right here, we have choices, especially for recycled water. Right now, what we need to do is build more pipe so that we can funnel the recycled water to all the golf courses, parks, large green spaces. So there are other more cost-effective. It's a balance act. So I think doing recycled water, doing a replacement of the turf, we're offering $1 for within the city of Los Angeles for every 1 square foot of grass you replace with California climate, type of plants. You get $1. And we're already talking with some of the school systems. They wanted to do a wholesale change of 40 acres at a time, all their landscapes, so that they can put put those changes. But those are a lot more cost effective than the ones relating to treatment of the salt water.
Thanks. Susan?
The issue with the water flow in the delta, and particularly with climate change, the predictions are that there will be a lot more winter runoff because of the warmer conditions. And so the issue for the delta is really flooding. And also the other consequences, the sea level rise. So those two together could have some quite negative effects on the delta in the winter. I think that the state needs to really consider developing a real-time monitoring capacity like they're trying to do with fires for these kind of flood conditions. For instance, when we had the flood in 2006 on the San Joaquin, or near flood, they really don't have kind of real-time information at the scale of the river systems that we have. So that would be something that certainly is technologically feasible and possible to get the information processed and out to the responding community quite rapidly, analogous to the wildfire work. The consequences in the summer are the lower flows than current, and how you manage the quality of the water and the water supply in the summer as it goes through the delta with the very low flows. It certainly will have a negative impact on the fish population. One of the considerations for the peripheral canal is to try to better provide water supply in that period. Although I don't, the problem right now is that we have a conflict between urban use, agricultural use, and environmental use in the delta, and we don't have enough water to go around.
So, a question from the audience is could you describe a little bit about your experience in Sacramento, to the extent that you've had it, talking to the state officials and so forth, and what you might recommend for those who are interested?
Well, I don't usually talk to the officials. I usually talk to the people at the resources agency who are pretty far down the line from making the policy decisions. But in terms of the state agencies that we've worked with, which have been Water Resources and the Department of Boating and Waterways and Fish and Wildlife, those agencies have been quite desirable of having university input and having the research done. They don't have the tools often in-house, and this is a real helpful component to it. I should say my lab also provides the spatial database for the state of California, the SERIES program. And so all of the state spatial data we've been putting online, and somewhere around 100 megabytes or so a day get downloaded, I think.
Yeah. Andrea, maybe you would comment a little bit about your experience now in Washington and how you see this interaction between the science data and policy is playing out.
Well, like Pete Warden, I'm always the optimist. He said maybe it's because he's not at headquarters. Maybe it's because I'm only half-time at headquarters. I'm still an optimist. I think the environment right now is very good in Washington, and so these committees are a great opportunity to interface with all of the agencies. I find they want to collaborate, and so let's make hay while the sun shines. But resources are scarce, but as long as we all have our clearly defined roles and can learn how to work together, I think as a whole we're all going to do much better.
John, a question from the audience is, are there specific mechanisms or forums now for local universities to work together on LADWP issues, and how can people engage in that process?
We do have a forum where, for example, we brought together all the universities, all the key players about 2 months ago, and worked together for about 3-4 weeks and wrote the stimulus package. But going forward, I think what we need to do is not just hold a 1 meeting or 2 meeting. What we need to do is really to look at creating a structure where problem can be identified at the utility level, then request expertise from all the universities to provide solution to those real-time issues. And through that process, maybe we can solicitate some of the experts and form a panel to review those suggestions and projects, and ultimately like to create some bridge funding to actually work on those problems. So it's more of a triangle arrangement. We will have identified problem, and then the universities or JPL can help us to solve it. Then we will set aside fundings. Under the state's public benefits program, utilities have to set aside 2.8% of their revenues for public benefits purposes. One of the 4 criteria is to invest in new technology and research. So we're trying to look into maybe set aside some of those funding to fund the projects, so that we can bridge the gap. And in addition to that, Google is here today, maybe Microsoft later on. We want also to engage the private companies. So from this particular issue, we may identify with a solution, and with the city and Department of Water and Power use it as a platform to offer, for example, rebates to help commercialize the product, and ultimately have the industries, private industry, to come to assist and really populate those discoveries or solution internationally. I think that's a model that we'd like to build, and hopefully once we set up that structure, each year we basically do a call for projects and have everyone submit their great ideas and help us to solve real world problems.
Another question to the panel from the audience has to do with the role of agriculture in water use in California. What are the prospects for changes in agricultural policies that would help with the water situation? And maybe, Susan, do you want to start with that, and anyone else can chime in?
Well, agriculture in California probably uses 80% of the water supply, so it's quite likely that's going to change. Over the years, well, since the late 70s, agriculture has gotten a lot more efficient with their water use. Many of at least the perennial crops, like the tree crops and the vineyards, mostly use drip irrigation to try to reduce excess water use. So there's a number of issues, but particularly in the southern San Joaquin Valley, where in the cotton fields and some of the other crops, they're very high water use, and they use furrow irrigation, which isn't very efficient. So I think there's a lot of potential for reducing water and also trying to reduce the runoff, which is a problem with increasing particularly nitrates, but contamination in the water supply.
John, do you want to comment on agriculture?
Not really. I haven't seen any farmlands.
Is the city of Los Angeles, San Diego, of course, entered into agreements to buy water rights from farmers. Is the city of Los Angeles also engaged in that?
Not right now. However, private developers, if they wanted to, we work very closely with the planning department. And we want to make sure whatever they plan, whatever they sign off, that there is plenty of water supply for them. But developer, especially in the future, probably will be able to approach the farmers to do a water rights exchange with them. Basic says you give it the right, then I can work out a deal with the city and pay some of the costs to the farmers.
So what might be the role of remote sensing in water management and agriculture? I know there was discussion, again, in the Washington Post this morning about the possibility of using the transevaporation estimates for individual fields to allow farmers essentially to bank water that they don't use in 1 year things that right now there's absolutely no incentive for farmers to not use their entire allotment. Maybe Susan, do you?
Well, the state is doing. The Department of Water Resources does do on a daily basis the potential evapotranspiration estimate for the state based on the weather conditions. So that system, they were using GOES satellite data, the geostationary satellite data, to get the net radiation, which is the main energy input that defines how much water is needed. So that provides kind of the maximum estimate of what should be. I mean, they can't use more than that amount. So I think that there's pretty likely to be fairly good evapotranspiration estimates for the statewide, not just for agriculture, because they really need to understand how natural communities are using water as well. But those things are really coming along. The state's implementing the weather forecasting WRF model, the NCAR's mesoscale climate model, and it predicts evapotranspiration, and they're running it at about 2 kilometer spatial resolution for the state on a daily basis, and then forecasting the potential evapotranspiration for the next 24, 48, and 72 hours. So that should help.
One of the interesting things, the Caltech grounds management here, as you notice, our campus is quite green with lots of grass. The city of Pasadena now limits watering to 3 particular days. But because they use smart sensors and these WRF-based analyses to estimate trans-evaporation, Caltech would like to water no more than 3 days, but different 3 days, because it turns out not to be perhaps a good day to water on a Tuesday. So these are the kind of things where regulations and planning and data have to come together to produce a better result. So that's interesting. Let's just turn away from water for just a minute, and I'd like to ask Andrea a little bit about the earth movement, earthquakes, land use planning in terms of the build-out of the state's infrastructure.
What specifically?
Well, how do you see that going,
planning.
and how do you we heard that the tunneling through South Pasadena seems to be perhaps being done in without a careful consideration and conversation with USGS. Is that is that true, and is that the current practice, and how can we, if so, how can we move beyond that?
I think that's the norm. Unfortunately, we're trying to change it. I know a lot of consultants that have worked on some of those jobs, so it's not completely in a vacuum because they're one step removed from knowing USGS people. But again, I think monitoring the ground motion is important. We had an earthquake at JPL that wasn't very big, but it wasn't on the Sierra Madre Fault like we would have expected. It was more likely on the San Gabriel Fault, which is thought to be dead. The other end of it, 2 days later, the pavement failed on the I-5 freeway at the intersection of that fault and another. And so these are things that we don't detect with the seismometers, but we could from the spaceborne measurements, and then we have to make sure the information gets flowed to the right places.
So in the planning of the radar mission, is there discussion going on right now about actionable products that will be able to be used by state local planning?
Yeah, we had a workshop actually last October, an applications workshop up in Sacramento. Gerald Bawden was a co-convener with me and John Rundle, and there were a lot of emergency planners, first responders, forestry people. There we have a report. It's on the web if you look for Decadal Survey Missions Destiny. But we still have to get to the next step, which is actually making sure it's implemented. And sometimes there are additional costs, and the other agencies have to step up to those additional costs if they exist.
So before we go to lunch, let's see if I have one more. Yes, I want to talk a little bit about, we've talked about space-based missions in particular, but many of the examples that were provided today involved what NASA calls the suborbital program. In other words, airplanes primarily, but also ground-based stations. And perhaps we could all comment, or those of us who are using data could comment on these the need for continuous or near continuous basis for long-term planning, and how the aircraft program might fit into that.
I actually have an opinion on that one.
Yes, go ahead, Andrew.
And that's that, as I said in the beginning of my talk, NASA is a research agency, and we need to transfer those assets. So Ames has this great IR instrument on the Ancanos UAV that flies around, but during these last fires it was in Santa Barbara. It's a research instrument. UAV SAR, chances are we'll have an earthquake here. If it's local, we'll fly it and understand the ground motion, but there's a good chance it might be in Greenland or on the East Coast studying the Gulf region. And so we need to make sure we can replicate these things to become operational systems, and the other agencies then need to pick those up. And that's a challenge we have.
I think in terms of snow, that would be very exciting opportunities to use things like unmanned aerial vehicles, where you might not need a snapshot of the snowpack every day, but instead of sending out surveyors once a month to get a few points in the Sierras, you send out this airborne platform to take measurements over much wider spatial scales. And I think at least that particular application would be well suited to non-space-based platforms.
I think for a lot of the environmental monitoring that needs to be done really could be best done by airborne platforms. It's an opportunity that you have to collect data at the time you need it, at the spatial scale that you need it, because usually global satellites have either a coarser spatial resolution than perhaps you want for answering specific questions, or they don't come around that frequently, because if they're high enough spatial resolution, they don't cover that much terrain. 2 decadal survey instruments that are being planned could be really supplemented at the state level with airborne systems. The Destiny that was just mentioned, which is a radar and LiDAR combination satellite, could really contribute to monitoring the Delta system. The other one is the mission for the what's called the Hesperi mission, which is a hyperspectral and a multi-band thermal instrument combination. And those would also definitely benefit both, for a large number of environmental problems in the state. And I think having kind of continuous monitoring is really not infeasible. At the beginning of the session, it was mentioned a lot of different countries are. Nigeria's got a satellite, China's got a satellite, India's got satellites, Japan has. The budget of the state of California, even though we're in pretty bad fiscal condition right now, is at the level of France or some other large economy. So it's not out of consideration that the state itself could provide a monitoring system that would complement NASA's instruments and provide the information the state needs at a value to the state that's affordable.
That's very interesting. I'd just like to end the panel discussion on a personal note. I took part in a NASA mission last summer that was done jointly with the Air Resources Board to do the first airborne evaluation of the greenhouse gas emissions of the state of California. So the Assembly Bill 32 required the Air Resources Board to quantify the current emissions from California. Now, for some things like CO2, we believe an inventory-based assessment is probably about as accurate as you can do. You know how much gasoline was delivered to the state. You know how much natural gas was delivered to the state. You can come up with a pretty good estimate of what the amount of CO2 is. But other things like methane, for example, which have a diverse biological sources, they have other sources that are poorly quantified right now. This was an opportunity for NASA and the Air Resources Board to partner to start to do this type of science. And that's going to be followed on next summer by a much larger effort, CalNext, that I think we'll hear about in the next panel. So with that, I'd like to thank the panel and we'll retire for lunch then. Thank you very much.